The last factor that can affect stability is vertical position of center of gravity. That's the last factor. And as you can see here, this time the arrow is pointing downward, which means the lower vertical position of the center of gravity is, the higher stability it is. So that we have two boxes here again. Okay, there are two boxes here. And then for the size of base supports between two boxes, okay, the same. And weights are also the same. But this box, first box, is higher than this box in terms of the height, which means this first box has a longer FA compared to the second box. So let's go back to this formula. So in this formula, okay, FA is denominator. So as FA increases, F will decrease, right? So if you go back to this box, since this second box has shorter FA compared to this box, okay, FA will be decreased for this box, which means F value will increase for the second box. That's why we can say this box, second box, has a higher stability compared to this box, because this box will require us to use more force to break the equilibrium. And also, as you can see here, the second box has a greater angular displacement to break the equilibrium, right? Compared to the first box. That's why here data 2, which is this one, is larger than data 1, which is this one. Which means, this one also has greater angular displacement to break the equilibrium. Okay, next kinetic concept is a moment of inertia. Again, this is a part of the last reading assignment. This concept is a little bit more difficult to understand compared to other angular kinetic concepts. That's why I put this one as your reading assignment. So since you have read already these concepts, so you should be able to better understand the concept of moment of inertia. Okay, moment of inertia. This is actually moment of inertia in angular motion. You learned mass. Mass is the moment of inertia in linear motion, but moment of inertia, this is a measure of inertia in angular motion. And then let me show you how we can quantify the moment of inertia. And then we have one figure here, and then this vertical line, this is a rotating the center, which means the axis rotation. So then this vertical line will generate rotation, as you can see here, this way. Okay, and then here, M, this is a small mass particle, almost negligible volume, but it's a very small mass particle. But still, this one has its own mass. Okay, and then R means separation distance between this mass particle and the axis of rotation. So this mass particle will rotate about this vertical axis. So something like this. Okay, rotation. And then here I means moment of inertia. Okay, so moment of inertia is equal to m mass times r, which is separation distance, squared. This is a formula we can calculate the moment of inertia. And then here, okay, moment of inertia is also defined as the tendency of an object to maintain the current state of angular motion. That's why this is the measure of inertia in angular motion. This is also defined as difficulty in changing state of angular motion. And the unit of moment of inertia is kilogram times meters squared, because unit of mass is kilogram and unit of distance is meters. That's why kilogram times meter squared. And actually, the moment of inertia is a scalar quantity, not vector quantity. This is a scalar quantity. No direction information is involved in moment of inertia. And here MOI means moment of inertia. Actual moment of inertia of the object is the function of mass distribution about the axis of rotation. Okay, so let me explain why this one is a function of mass distribution about the axis of rotation. Okay, right here, for example, we have the same bed here, A and B, A and B, and then we have a weight rings, okay, on each bed. Okay, these two are the same as well. And then let's assume that this part right here is the x rotation, and assume that we can rotate this bed about this the x rotation and rotate, okay, like this. Okay, if then which one is easier to rotate the bed? Okay, B is easier to rotate compared to A, because so since wedge ring is located right here, okay, a bit closer to the axis of rotation, that's why more mass is located closer to the axis of rotation for this bed B compared to for bed A. That's why this is a lot easier to rotate. What if we are holding now this part, okay, not here, but here, end of this bed, which means this point will be serving as the axis of rotation. And then again, rotate these two beds again, okay, this way, okay. If then, which one is easier to rotate? This time, bed A will be easier to rotate compared to bed B, because since this part is the actual rotation, okay, for A, bed A, more mass is distributed to the actual rotation for bed A compared to for B. That's why depending on how mass is distributed with respect to the actual rotation, okay, moment of inertia can be changed. And then I'd like to introduce now the concept of radius of gyration. Again, this is again part of your the last reading assignment. Okay, so theoretically, as you can see here, even single bed here, this single bed is composed of a number of mass particles. Here, mass particle number 1, mass particle number 2, mass particle number 3, and etc. And then in order to calculate this moment of inertia of this bed, you have to add all small mass particles moment of inertia, theoretically. But actually that's impossible. Theoretically it's correct, but it's impossible to find all small mass particles moment of inertia and then add them up. That's why to simplify the calculation, we have to use the concept of what? Radius of gyration, which is k here, the k. So that instead of combining all small mass particles moment of inertia, now we can use the single value of radius of gyration, which will simplify our job a lot easier. Here, so radius of gyration is defined as the distance from the axis of rotation to a point where the body's mass could be concentrated without altering its rotational characteristic. Excuse me. So, so we have one object here. Okay, as I mentioned, this object consists of a number of mass particles. But instead of combining all small mass particles together, now we will be using this single value, which is the rate of gyration. Okay, so that from now on, whenever we calculate moment of inertia, so we can use this formula. Here, I means moment of inertia is equal to mass times rate of gyration squared. And then here ROG means the rate of gyration. So rate of gyration does not show the location of the center of the mass. Although this one reflects the rotational characteristics, this one does not show the location of center of the gravity or center of mass. Okay, let's compare the rate of gyration between these two, okay, and then between these two. Actually, these two are the same arm, and these two are the same legs, okay. So here, this situation is this, okay. He is running with the leg knees flexed extended, normal running technique. But this one, he is running with a straight leg. If then, which one has a greater or longer radius of gyration? Okay, here K1 means radius of gyration of the thigh, and then K2 means radius of gyration of shank with respect to hip joint, and then K3 is the radius of gyration of the foot with respect to hip joint, and then same thing for this leg. Okay, so as you can see here, this one has a shorter K4 or 3 radius of gyration compared to this one, which means this one will generate a smaller moment of inertia compared to this part. That's why when you run with here with the knee, excuse me, flexed extended, okay, you can run more effectively compared to when you run with the leg straight. Then another example here of a rate of gyration. Now you are now rotating your forearm. This time you're rotating this forearm about the elbow axis, the actual medial lateral axis. Okay, so that you are keep repeating flexion, extension, flexion, extension. If then your rate of gyration of your forearm will be this long. Okay, but this one you're rotating the forearm, but this time longitudinal axis. So you are keep repeating pronation, supination, pronation, supination. If then this black line will be serving as actual rotation. If then you are gonna get this K here, which is a lot shorter than this K. Okay, so that you can determine that when you rotate your forearm about the longitudinal axis, you can rotate your forearm a lot faster than when you rotate your forearm with respect to medial lateral axis. Again, when you do a flexion extension motion. Because this one has a shorter rate of gyration compared to this rotation. Here, moment of inertia and rate of gyration of the body is a partial dependent. Okay, assume that we have same diver here, same diver, and he is in the air. Okay, this is a tuck position, T-U-C-K, tuck position, the pike, and then layout, and then giant swing. Okay, so among these four, which one has the shortest rate of gyration, which will generate the smallest amount of moment of inertia for a given body? So as you can see here, you can easily find that this one, tuck position, will have shortest rate of gyration, which will generate the smallest amount of moment of inertia. And then if he change his partial from the tuck to pike, okay, he will increase his rate of gyration slightly, okay, which means he can generate a bit larger moment of inertia for this position compared to for this position. Okay, same thing for this one. Okay, he now extended his body fully, so layup position. So he again increased his rate of gyration from the pike to layup position, so that he increased the rate of gyration, and also one more increase, okay, when he changed partial from the giant swing to from the layout to the giant swing. So again, overall, this one will have shortest the rate of gyration, and then this one will have the longest rate of gyration. Okay, next topic is torque revisited. Okay, I'd like to revisit the torque. Okay, as you learn, torque is defined as the loaded force that causes the angular motion. So we can quantify the torque by multiplying force times momentum. But here, there's another way of calculating or quantifying torque. So we can also get the torque here by multiplying moment of inertia by angular acceleration. If we multiply these two, we can also get the torque. Okay, so I means moment of inertia, and then alpha means angular acceleration. Again, which means there are two ways of calculating torque. Okay, force times momentum, and here moment of inertia times angular acceleration. But actually, these two methods, two ways, will give us the same answers. So you don't have to worry about which one should be used, but both of them will give the same answer. I'd like to introduce another way of calculating the torque. Okay, and then we can also apply Newton's laws of motion to the angular motion. So you learn three Newton laws of motion in the linear kinetics chapter. But angular kinetics chapter, in this chapter, we can also use Newton's laws of motion as well. Okay, so let me apply Newton's second laws of motion to the angular motion. Okay, so I can simply read this one. An external torque acting on a body generates angular acceleration. In linear kinetics, the second laws of motion was like this. A force, external force acting on a body generate a linear acceleration. But this chapter is angular kinetics. That's why you can simply replace linear with angular when you apply Newton's laws of motion to this angular kinetics. And then next concept is angular momentum. Angular momentum. But before I start this angular momentum, so I'd like to go back to linear momentum. Because if you understand linear momentum, so you should be able to easily understand angular momentum. Okay, so linear momentum was defined as the amount of linear motion or quantity of linear motion, okay, which is a vector quantity. Okay, so angular momentum, you can just replace linear with angular. So quantity of angular motion, that's the angular momentum. So total amount of angular motion performed, that's the definition of angular momentum. So you can calculate angular momentum by multiplying moment of inertia by angular velocity. Again, if you go back to linear momentum calculation, so we can calculate linear momentum by multiplying mass times by linear velocity. Okay, very similar. Okay, mass is again measure of inertia in linear motion, and as you learned today, the measure of inertia in angular motion is a moment of inertia, and then linear velocity in linear momentum. But since we are talking about angular momentum, you have to multiply this one by angular velocity, angular velocity. So here, that's why here I put this one to have a bridge between linear momentum and angular momentum. Okay, here h means angular momentum is equal to moment of inertia times angular velocity, which is very similar to linear momentum is equal to mass times linear velocity. And then as you learn, so moment of inertia will be mass times rate of gyration squared, so k squared, and then omega is angular velocity. And the unit of angular momentum is kilogram times meter squared per second. So kilogram is coming from mass, and then meter is coming from rate of gyration, and then the per s will coming from the angular velocity. Actually, the unit of angular velocity is radian per second. But as you learn, the radian is a dimensionless unit. So that you can ditch the radian. If then we can only get per second. That's why the unit of angular momentum is kilogram times meter squared per second. Okay, let's go over one simple example of how we can calculate angular momentum. Here h is angular momentum. So let me just briefly show you. Okay, mass times, right? Okay, 10 times, okay, k squared, so point 2 squared, lastly times what? So angular velocity. So mass times rate of gyration times and angular velocity. Gyration squared times and angular velocity. So it will be angular momentum. So I will leave the rest of calculation. You can simply calculate this by using calculator. This slide will tell us about angular momentum conservation. Okay, you learned linear momentum conservation from the previous linear kinetics chapter. This is very similar to that concept. So the angular momentum conservation means a total angular momentum of a system remains constant in the absence of external torque. Okay, here conservation means something remains constant. Here angular momentum remains constant unless we are having a torque from outside. Okay, here h represent angular momentum as you learn, and then it remain constant. And then the angular momentum calculation formula here. So moment of inertia times angular velocity, this will remain constant. So that for a given angular momentum, constant angular momentum, as I increases, okay, omega angular velocity should decrease, and vice versa. Which means as I decreases, angular velocity should be increasing, because we have a constant angular momentum. So if you take a look at this figure here, so you have a diving example again. Okay, he is here start diving from layout position, and then he changed his posture from layout to tuck, and then tuck to layout again. So I can divide this whole diving motion into two phases. Okay, from here to here, you can say first phase from layout to tuck, and the second phase will be after this. So tuck to layout. And here h, here angular momentum, moment of inertia, and angular velocity. So while we can maintain the angular momentum because he's in the air, as I decreases, okay, angular velocity increases, and then as I increases, angular velocity decreases. Okay. So if you go back to figure up here, okay, when he changed his posture from a layer to top, I can say first phase, okay, he reduced his rate of gyration, which will eventually reduce his moment of inertia. If then his angular velocity will be increasing. And then during the second phase, from top to again layout, if then he is increasing his rate of gyration, okay, that's why his moment of inertia will be increasing. If then his angular velocity will be decreasing, okay, because we. Let's go over one example of angular momentum conservation. This example is highly important for your exam. So here there are two positions here, but still he is in the air. This is a diving situation. Position 1 and position 2. Okay, and then these information provided for the position 1, and then lastly we need to calculate his angular velocity at position 2. Okay, again, as I mentioned earlier, this is example of angular momentum conservation because he's in the air, so that just make sure that angular momentum at both positions are the same. Okay, keep that in mind. Okay, let's calculate angular momentum at position 1 first. Okay, if then let me simply here mass 60 T times k squared, right? So 0.5 squared, this is the rate of gyration, times 4. So if you calculate this using your calculator, answer will be 60 kilogram times meter squared per second. And then this angular momentum must be the same as at the angular momentum at position 2. So I can bring this value simply here. Okay, angular momentum at position 2 is equal to mass, again the same, 60, right? We are dealing with the same participant. He just changed his posture times. Now look at his K, rate of gyration at position 2. He reduced, right? So that 0.225 squared times omega. Okay, I will leave the rest of calculation to you. Okay, actually, if you calculate this value, omega will be 16 radians per second. Okay, so if he changed his posture from layout to top, okay, he will be increasing his angular velocity at a rate of 16 radians per second, which is a lot faster than this angular velocity at position 1, because he reduced his rate of gyration by reducing the rate of the gyration. If then it will allow him to increase his angular velocity at position 2. Again, the bottom line is angular momentum at position 1. Okay, this is the last slide of this chapter. Okay, transfer of angular momentum. Okay, so while maintaining the same amount of angular momentum, okay, overall angular momentum remains constant. So you can maintain the same amount of angular momentum, but angular momentum of each body part may change. They can transfer their angular momentum each other. So angular momentum, for example, upper body can be transferred to angular momentum of the lower body and vice versa. And we have one figure here to better understand transfer of angular momentum. Okay, he's also doing diving here. So here layout to pike, and then pike position to the layout. And then here H total means the total amount of total angular momentum. And then solid line means lower body angular momentum, and dotted line means upper body angular momentum. And then they are transferring angular momentum each other. So that let's go back up here. If you take a look at the diving figure from just here to here, layout to top, if you take a look at his lower body, he's not moving his lower body that much, whereas he's moving upper body a lot, okay, compared to the lower body. That's why he has a higher angular momentum coming from upper body, but he has a lower angular momentum from lower body. But after this point, from pike to layout, okay, look at his upper body. His upper body, okay, he's not changing his upper body movement that much. But if you take his lower body from during this phase, he's just changing lower body motion a lot, okay? Through this way, right? That's why he is showing very high amount of angular momentum from lower body, and then low with a smaller amount of angular momentum from upper body. Again, while maintaining the same amount of total angular momentum. So angular momentum of upper body and lower body, they can transfer angular momentum each other. Okay, please don't get confused. Don't get this confused with the previous angular momentum conservation figure. They are very similar to each other, but they are different the figures. Again, we are all done with the angular kinetics chapters.